So let's look at our first rule of differentiation, right? It's the most basic, it's the most commonly used, and it's called the power rule. And it's a rule that we discovered when we differentiated functions from first principles. So this is something that you learned all the way back at IGCSE, and now hopefully after watching the last couple of videos, you understand where the idea for the power rule came. So the power rule says if you have some function y equal to some constant times x to the power of whatever number, then its derivative, so I've got dy by dx is the derivative, its derivative, its gradient, is equal to a times by the power of n, x to the power of n minus 1. Okay, and the easiest way to remember the power rule is by always just saying the saying in your head, multiply by the power, then reduce the power by 1. Okay, and that's going to work in a multiple number of ways. So let's just do these examples to remind ourselves what the power rule is. So here we have a, and we want to differentiate with respect to x. So when we differentiate with respect to x, these are expressions, they're not equations. So when we differentiate with respect to x, we are asking, we want d by dx, the derivative with respect to x, of x to the power of 5. And what is that equal to? So we have x to the power of 5, so we're going to use the power rule. We're going to multiply by the power, and then we're going to reduce the power by 1. And there's our derivative. Right, now we have 1, so we want the derivative d by dx of 1 over x cubed. Now, I can't differentiate when the power is on, or the variable is on the denominator, so I'm going to use index notation to bring it up to the top. So to bring that up to the top, this is going to be x to the power of minus 3. All right, and now I can differentiate it like before. I'm going to first multiply by the power, and then I'm going to reduce the power by 1. And I need to be careful here because this is a negative number. So when I reduce negative 3 by 1, it becomes negative 4. Right, C, we want the derivative, so d by dx of the square root of x. And again, I can't differentiate when it's written like that, so I need to use index notation to change that into something that I can differentiate. So we should remember that from our index laws, the square root of x can be written as x to the power of 1/2. And so now I'm just going to differentiate using the power rule. So I'm going to multiply by the power. So the power is 1/2. And then I'm going to reduce the power by 1. And so that's going to become negative 1/2. Okay. Now we can tidy this up, right? We can also tidy up the previous one. So B, we could have tidied up by saying we have this x to the power of minus 4. So instead of writing it as a negative power, we could have just moved it back to the denominator where it came from. And so we can do the same thing over here, where we can move the x down to the denominator with the 2, and it'll just become positive 1/2. And we can further make this tidier by remembering that all x to the power of 1/2 is, like we changed before, is just the square root of x. And so we'll get 1 over 2 square root x. And let's do the last one here. We want the derivative of 3. Right, if you want to calculate the gradient of a constant number like 3, well, if we have a constant doesn't change, and so it has no gradient. And so the derivative of any constant number is always going to be 0. Another way of thinking about this is to remind yourself that sometimes there's just information that's hidden. There is an x over here. It's just x to the power of 0. Okay. anything to the power of 0 is just 1, and so x to the power of 0 would be 1. So if we use the power rule on this, the power is 0, so we multiply by the power, and then we reduce the power by 1. Now it doesn't really matter if we reduce the power by 1, because anything multiplied by 0 is 0. So either way you think about it, the derivative of a constant number will always be 0. All right, let's move on to something a little bit more involved. So here we have an entire expression full of x. And all we need to remember is that the derivative of a sum, so here we have a whole sum, even though they are negatives, remember it's just adding a negative number. A derivative of sum is just equal to the sum of the derivatives. Okay? So in other words, if we have some function u of x plus v of x, the derivative would just be the derivative of u plus the derivative of v. Okay? So here we are differentiating with respect to x. Right? This is not an equation, it's a function, and we're differentiating 2x to the power of 5. I'm going to change everything into something that I can differentiate. So minus 3x squared is fine. This plus 1 over 2x cubed, I can't differentiate that. I need to change it. So this is going to become plus x to the power of minus 3 over 2. And then we have plus 5 over the square root of x. I need to bring that up to the top, and I need to change it into index notation. And so I'm going to have 5 x to the power of minus a half. Okay, so the minus is because I brought it up, and the half is because it was the square root that I've changed to index notation. And now, even though I have a whole bunch of expressions, it doesn't matter. I can treat each individual expression by itself, because the derivative of a sum is just equal to the sum of the derivatives. So I'm going to differentiate each of them and add them together, essentially. Okay, so we're going to use the power rule. So here I'm going to multiply by the power. Now I'm multiplying by the power, but I must remember that I multiply the power by anything that's in front of x as well. So when I multiply by the power, I'm going to get 5 times 2, which is 10. And then I reduce the power by 1. And once again, here we have 2. And we're going to multiply 2 by the number in front. And don't forget that the sign is attached to the number to the left. So I'm going to take 2 times minus 3, and I'm going to get minus 6. And I'm going to reduce the power by 1. And we don't write the power of 1, so I'll leave it as is. Okay, the next one, I'm going to do the same thing. I'm going to multiply by the power. The power is minus 3, right? And we have this over 2 as well. X, and I'm going to reduce the power by 1, so it's going to become minus 4. And then finally, the last term, I have this minus a half, so that's the power. I'm going to multiply by the power, so I'm going to have minus a half, and I'm going to multiply that by the number in front of x, which is 5. So I'm going to get minus 5 over 2, and then I'm going to reduce the power by 1, which is going to be x to the power of 3 over 2. Sorry, negative 3 over 2. And we can leave that expression as is. We could tidy it up by moving these powers to the denominator. It doesn't really matter. So it depends on what the question asks you. All right, now let's look at some examples of where we would use the gradient function. So here I have some function, all right, it's the gradient is y, or the, sorry, not the gradient, the function is, or the curve is y equal to 3x plus 2, 2x minus 1. And if we think about this, all this is a quadratic. And what we're asking is what is the gradient at this point? Okay, so if we want to find the gradient of a curve, so here we have a curve y equal to 3x plus 2, 2x minus 1. I want to know what the gradient is at a certain point. So what I need is a gradient function. So we haven't learned to do the product rule yet, because this is a function times by function, but this is a simple function times by function, which I can just expand and turn into what we would recognize as a quadratic. So we're going to get 6x squared, and then we're going to get plus x, because we have 4 in the middle and minus 3 on the outside, and then minus 2. And this we should recognize as a quadratic equation, right? Now, if I want to find the gradient, I need the gradient function. And when we have an equation y equal to x, then we call the gradient function the derivative, which is just dy on dx, which is change in y on change in x. So the change in y and on change in x is equal to, and once again, we use the power rule, so multiply by the power, multiply by the number in front. So we're going to get 12x, reduce the power by 1, I end up with 1. Then I'm going to differentiate x. Remember, x has a power of 1. So I'm going to multiply by the power, and then I'm going to reduce the power by 1. So I'm going to get x to the power of 0, and anything to the power of 0 is just 1, and so x is going to disappear. And then finally, we have minus 2. Minus 2 is a constant, and when we integrate any constant, it differentiates into nothing, and so it will disappear. So now we have our gradient function dy by dx. Okay, so what I can do now is I can input values of x. So I can input any value of x, and what will come out is the gradient. Okay, that's an important thing to remember. The gradient comes out. So let's say, well, when x is equal to, well, we wanted to know the gradient at minus 1. So when x is equal to minus 1, dy by dx is equal to 12 times minus 1 plus 1, which is equal to minus 12 plus 1, which is minus 11. So the gradient at minus 1 is minus 11. In other words, it's changing by 11 units down for every 1 unit it grows across. Okay, because remember, minus 11 can be written as minus 11 over 1. So this is rise over run. So we are rising down by 11 units for every 1 unit. So that's quite a steep gradient. But that's just an example of where we would use the gradient, right? And more importantly, we've now had a good look at how to use the power rule, not only to find the gradient function, but if we have a expression with multiple terms where we can use the power rule on the terms separately. Okay, and we are going to start learning more rules as we go along, but the power rule is generally the rule that we use most often with the chain rule, which we're going to learn next.